and it is such a things that if you do not know the underlying flavor, that is what is working behind the computer, then the interpretation of the results is becomes quite difficult for yourself. So I'll try my best to give you the things, not going in detail mathematics, but some kinds of understandings, that is with the help of some small flavor of mathematics, little flavor of mathematics rather. So I'll try my best, and if you have any questions or any queries, just interrupting me and ask. Feel free to ask me yourself. That is any kind of queries from yourself. And I will start initially with some, that is the understanding of the process. What is multivariate? I'll start it from here. So then I'll go to the one part. There are several things related with the multivariate analysis, but I actually have to do the thing, that is I have to deal with principal component analysis. And uh, so let's start. I think my voice is audible, na?
Yes, sir.
So just 1 minute. The screen is visible to all.
Yes, sir.
Okay, okay,
Yes, sir.
okay. So multivariate is the main area today, but what we want to do, that is basically one part of it, that is the principal component. So first you may ask the question that why multivariate, because those I think all of you are related with some kind of research, and we deal with many variables. So the relationship between such variables uh, is a significant part, and not only the relationship among the variables. Uh, suppose within a set of lot of variables, significance of any particular variable, it is such an area, that is, you may call it is a mixed bag. It is a mixed bag. So that means where we are dealing with all the variables and their relationship, and simultaneously the significance or the importance of only one variable, that is also important to us when you are dealing with multivariate. So now the objectives, basically, what is the objectives of multivariate? For example, those who are related with researches on social science. Suppose in a socio-economic survey, you collect various informations, various data sets to explain, and you find out. Suppose you are interested to find any regression type of relationship, that is whether there is a cause effect kind of relationship or this. So to do this, is all the independent covariates or the variables what data you collected are important, or are important in equal percentage, or equally significant, equally important? That is the important question. So it is not necessary. Not all the variables are significant by the same percentage or same amount. So basically, you have to identify which variables are more important, which are quite less. That means some kinds of ranking of the variables. Then you have to introduce those important variables for our research, not that is excluding the less important variables rather. So we need a structural simplification. And structural simplification is what it is basically leads to data reduction. And that is what sacrificing the variables or valuable information for better interpretation. This is the structural simplification. So using the total data of several variables, we will measure the response against one common questions, and we identify the important variable. This is the important thing. That is, data reduction means using the total data of several variables. We collect their responses and find out which one is more prior to us, and then what we are doing in generally, that is developing an index, that is the index of performance of each variable, and from that performance you can find out that which variable is important and which variable is less important. So this is one kind of things, and basically the factor analysis or PCA is deal with this part. And there is another kind of this is one kind of grouping, and there is another kind of grouping, and today this is not our task, that is the clustering. And I'm not entering into the clustering kinds of things because it is not part of our discussion. That is the other way, that is sorting of groupings. Actually, this means that is sorting of groupings. So and it related with cluster, developed string process, visual representation, these kind of things, grouping of the variables there. So whatever from these kinds of structural simplification or data reduction technique or sorting of groupings, what is the next step in research? That is the next step follows from here. That is investigation of dependence among the variables. I mean, how variables are dependent. That means dependent on one and each other. That is natural. That is natural relationship among variables, and this is basically leads to nature of relationship. And this kind of nature of relationship means what? That means from that relationship, what we actually extract, that is the factors responsible for changes or for influence. This is the first thing. And second thing is measurement. This is the first one. Second one is measurement. And third one is measurement of the variable. And third one is measurement of character, measurement of the character, specific character within the variables. And fourth one is measurement of association between the variables. So from these four kinds of thing, what we are actually going to do under the multivariate, that is predictions. What will happen if this model is working, these kind of things. So on the basis, when I am going to make the predictions, and the basic statistics, that is here actually we using the inference, that is hypothesis testing, that is experimental technique from the observational results and its interpretations. These are the things. So this is the basic working style, basic initial working style of multivariate. So let us start with an little understanding better. That is, suppose I'm started with a socio-economic data, and the socio-economic data, that is there are the social data, there are the demographic data, and there is the economic data of some village you collected about the individuals, about the households information. So the variables, for example, sex, suppose it is x1, for example, age, suppose it is x2, for example, caste, suppose it is x3. By this way, suppose we are collecting different informations about the households, and the data set is this. Now, when you get the information, suppose about 100 households, then what do you actually, you put the data in the Excel, and what do you actually get? You get a matrix, and the matrix looks like this. That means it has some rows. The variables are here, x1, variable x2, and so on. Suppose this is the xk variable. K is a number. That means if you collect the 15 variable, k is 15. If you collect the 10 variable information, k is 10. So each values are there. Specific values are there. So all values are there, and you get a data matrix. This is called data matrix. Okay. So when you get the data matrix, then what do you have to get? That is, we can find out the different descriptives. For example, what will be the mean? For example, what will be the mean of this? That is x1. You can calculate. You can calculate this mean. You can calculate this mean. So you can calculate this. So look, you can calculate this. So when you get the mean, so you can construct a mean matrix. So you can construct a mean matrix of the variables by these values. That is, x1 bar is the mean of the first variable, x2 bar, and xk bar. This is we call mean matrix. Okay. Similarly, from the same x matrix, from the same these values, you can find out the variance of the first variable. You can find out the variance of the second variable. You can find out the variance of the kth variable. You can find out the variances. So we actually know what is the, we know this is the, if this is the original matrix, and we know the formula of variance, and that is defined by such a way, that is, suppose it is first variable, I write it as in this form is 1 1, or you may write in some book it is write as s1 square, and the formula is 1 by n summation of xji1 minus x1 bar whole square. This is the formula of variance. That means what? That is you know the mean of this set. You know the mean of this set, and then you take the difference of each and every values of this x1. These are given from that mean, and make it square, and sum it, and then divide it by the 100. That is, if it is 100 households, so you divided it by 100, and then you get the S11. Okay, this. So similarly, you can find out S22, and by this way you can find out different variances for all the k variables. So all the k variables you have to find out S11, here S22, and SKK, or S1 square, S2 square, and SK square. Not only the variances. Look, we can find out the association between x1 and x2, between x1 and x3, between x2 and x3. By this way, we can find out different combinations. So if I make the combinations, then if I find out the association between x1 and x2, look, if I consider only these two variables in my data set, suppose only these two variables, then what we can calculate, that is its first value and its first value. Then I make the difference of this value from its mean and difference of this value from second variable mean, and then multiply it and then divided it by 1 by n. Then you can get the covariances. If I do this, then I get the covariances, which is actually written by mathematically. These are not important. This software or the computer, these are actually calculating this. The value is this. That is x j1. Suppose it is between 1 and 2. So it is j1 minus x1 bar and x j2 minus x2. So this is the covariance. So by since there are k number of variables, so we can find out different combinations. And if we make such a table, look this, that is variables. We consider x1 minus x1 bar. That means x1 is what? x1 is the values of the first variable minus its mean. That means from all values I make the difference. Similarly for the second variable. Similarly for the third variable, and by this way for all the variables. If I make a column, if I make a row, and similarly if I make a column, then what this thing shows to us? This area is what? This area is the multiplication of these two. That means x1 minus x1 bar into x1 minus x1 bar, which is this term. Look, that is xj1 minus x1 bar square, because both are same. So you write here, S11. But here, but in this place, what do we write? This is the multiplication between this one and this one. That is x1 minus x1 bar and x2 minus x2 bar. So we can write here it as S12. There is a covariance between x1 and x2. And by this way, this is the covariance between 1 and k. Similarly, here, when I'm interacting this, that is this place, this is between x1 and x2. So we write it we write it as S21. Screen is visible to all?
Yes, sir.
Yes.
And here in the second place, in this place, look, it is what? It is the variance of x2, and we write it as S22. And by this way, this is S2k. And if I extend this, then it becomes SK1, SK2, and so on, SKK. Look at this matrix. Look at this matrix. Look at this matrix. This term, this diagonal term, are all the variances. And the off diagonal term, this term, are the covariances. Where it is? These all term are the covariances. And you know what is S12? That is the S21. What is S13? That is the S31, because multiplication is same. If you multiplied x1 with x2 and then x2 with x1, that thing is same. And this matrix is known as covariance matrix, variance covariance matrix, and sometimes we write it as variance covariance matrix. Okay, it is. So is the sense of the matrix is clear? How from the data set, how it is estimated? I think it is okay. Before going to PCA, these are basic ideas, because it is very much deal with this kind of matrix, and the importance of the matrix is important. Now, one thing another is important, that is the correlation coefficient. And I think you heard this term. This is nothing but just I change these things, that is screen is visible to all. Okay,
No, sir.
1 minute just. Is it now visible?
Visible now, sir.
Yes,
Visible?
sir.
Is it visible?
Yes, sir.
Okay, okay. So look, this is the variance covariance matrix. Earlier we derived this. Now, if I just change these things, what is this? These are the just deviations from the mean values. If I just change these values by what? That is this. This was what? X1. Look at this. This is what? That is X1 minus X1 bar. It is measured here. And it is also the same thing is here. Same thing is here. That is, I just rewrite it. X1 minus X1 bar here. I'm not now measuring this only. I'm measuring this divided by S11 and this also divided by S1. Sorry, not S11, root over S1. That is the standard deviation. That is X1 minus X1 bar divided by S11. And this will be X2 minus X2 bar divided by root S22. And this will be this divided by root SKK. And this is divided by S22, root S22. And this is divided by root SKK. If I measure this, then look, what are the elements becomes? Look, what are the elements of this area? This, which one will be this? That is x1, xi, x1 values minus its mean. Again x1, that means the s11 divided by root over s11 into root over s1. That means this value becomes 1. And you know, this value becomes 1 because the denominator is s11 and the numerator becomes is also a summation of x1 minus x1 bar square. That is the s11. So it is becomes 1. But here, when I'm coming to here, that is in this place, it is the multiplication between x1 minus x1 bar and x2 minus x2 bar. That is, we know s12. S12 divided by 1 is here, it is S11 root over S11 and another is root over S12. And that is, we know what? Correlation coefficient, that is R12. Okay, it is. So from each such multiplication, and this becomes R1K. And similarly, if you do here, the same thing, this becomes R21, this becomes 1, and this becomes R2K. And by this way, RK1, RK2, and by this way, this is 1. So this matrix, when it is formed, then this matrix is known as correlation matrix. Look at the diagonal value. These are all values because it is a self correlation, like a correlation of x1 with x1. That is all. That is why it is 1, 1. That is everywhere it is 1. And that of diagonals elements, these are the correlation. That is, you know, what is R12, that is also R21. What is RK1, that is also R1K. What is R2K, that is RK2. Same things. So sometimes in the software, what they are doing, they write the correlation matrix by this way. That is by this way. Sorry. That is by this way they are writing. That is 1 values, some values, again 1, then some 2 values, again 1, and by this way, last value is 1. Because why it is not written? This part is not written because it is same. It is the same values here, so it is not written in the software results. and that is the interpretation of correlation matrix. So you can take simple examples and you can do the things. Okay. Now multivariate, when I am dealing, this is one important aspect of multivariate. These two are important, very important thing. That is the covariance and the variance, covariance and the correlation. But not only these parts, even any individual data. Suppose, for example, what you are doing in your those who are not doing the PhD, they know. Suppose they are doing some work on primary research, then they will, what they will do. Suppose it is some based on some socio-economic survey or these kinds of things. They have to collect the primary data. So what they, suppose it is a district level work. Suppose, so what they will do, they first identify the districts, that is as per their research question, they identify the districts, and then from the districts they go to blocks or may subdivisions be there, and from blocks to go to villages, and from villages they go to the households. These are the steps. So this is already given to you. Suppose it is a district level work, so districts is chosen by you already. So you have to choose the blocks which are properly represents the districts. Then you have to choose the villages which is properly represent the blocks and the districts, and you have to choose the households which is also the proper representation of the data set. So then you ask them the different questions, which are the different variables of you, as per our earlier matrix. That is, these are the variables. These are the variables in your questions. So now my question is this. So suppose one information is at least information is collected from here. Suppose from any one individual, uh, that is, the information is xij. Any information is xij. So this xij is a particular information of a particular households. Look, these households belongs to some villages of this district, and that villages also belongs to some blocks of the districts. So the districts have some average values of these variables. Suppose the variable is age. Suppose this is the age. So districts have some specific average age, and blocks have some specific average age, and the village has some specific average age, and your data set have actually receives one age. So how this age is related with these levels? This is an important question of multivariate. So that is when you collect this information, when you collect this age informations, you have to face some population. So this population is collected from some villages, from particular villages, and that village is a part of a block. So if I started with block, so there is some mean of the age of the people of a particular block. So how this population, if I consider this as a population, so how this population mean is influencing this particular individual's age. This is the important linking of the multivariate. So we can write the relationship is by this way. That is, suppose a specific age is xij. That is the values of the observation. How it is related with population mean, that is this is the population mean. This is how it is related with population mean. Or you may call it is mu I. How it is related with population mean. And in econometrics there are some correctional factors, observation, treatments effects, you may call it that is error or the white noise in time series. So this is the part. Now this population mean, suppose it is you considered as a from where the age data is collected, the mean of that observations. How this population mean is related with overall mean, how this population mean is related with overall mean, sorry, overall mean, say may you call it mu, and plus some uh, treatment effect. That means what is treatment effect? That is what is the difference between the block mean and the village level mean. That is identified. So exact relationship when you are dealing with the data, the exact relationship, exact value of a particular variable, what by what we are written, that may be interpreted as this is overall mean plus treatment effect. I'll come some example and show you how it is working, and plus the observational error. So, and this is actually the mu I. This is the population. Or you may call it when you consider dealing with a sample, you may deal with, say, you may rewrite it. I'm dealing with the population, so I'm telling you the population mean. So this is the um, components of an observations and the age of a particular household is this. It is influenced by the overall mean. It is influenced by the treatment effect, and it is influenced by the that is unobservational facts, random error. So overall mean, treatment effect plus random error, these three things produce a multivariate level of data or any kind of data. And in if you already do the ANOVA, you know that kind of representation is actually we are dealing with the ANOVA. For example, suppose I'm giving you just for better understanding. Suppose consider three samples I collected. I collected three samples, and what are the informations? Suppose first population, first population, I have collected the informations like, suppose it is some scale like that is Likert scale, informations. The informations are from the first population. Suppose these are the values 969. From the second population, the values is suppose 0 and 2, and from the third population, the values is suppose this. So what is the population mean? We just calculate 9 plus 6 plus 9 plus 0 plus 2 plus 3 plus 1 plus 2 divide by 8, and you get this is 4. Okay, this is 4. So this is the overall mean. This is the overall mean. So actually, for example, suppose from the what is the mean of the first population? That means you have to 9 plus 6 plus 9 divided by 3, 0 plus 2 divided by 2, 3 plus 1 plus 2 divided by 3. This is the mean of the third population. So we can explain, we can write each and every observation by this. What is the way of writing? The way of writing, for example, suppose it is third population. The third population, uh, the mean is what? 3 plus 1 plus 2. That is x31. Suppose, for example, the value is x31, and what is the values of x31? That is 3. And that is written as in the form that is overall mean. So what is the overall mean? That is 4 plus what is the mean of these 3? That is 3 plus 1 plus 2 divided by 3, 6 divided by 3, that is 2. And you write here that is 2 minus overall mean plus the individual values 3 minus that is the group mean, that is 3 to 2. So ultimately what you get, you get that is 4 plus minus 2 plus 1. That means you get it as 3. So this is the way how we have to write the data, considering all the observation. That means what you are following, That means x31 is written by this way, that is the individual value uh, plus the in the overall mean plus the group mean minus overall mean and plus the individual value minus the group mean. This is the way. And this is what? This is this is the overall mean. This is the overall mean. And this is the estimated treatment effect. This is the treatment effect. And this is what? This is the residual. This is the explanation of multivariate data. When we are dealing with the multivariate, each and every data can be interpreted by this way. That is observation. Observation is equals to overall mean plus estimated treatment and plus residual. So this is there is a huge literature on the basis on this multivariate.
Mm. Excuse
Hello.
me, sir. That is observation is equal to overall mean plus estimated treatment plus
Yes,
what?
that is estimated treatment effect. That means you look what is estimated treatment effect. What is this?
Then what?
X3 bar. X3 bar is the mean of the third population.
Yes,
And how it is, that means suppose it is the village. Suppose
yes.
it is the information of a village. And this is the informations of a block, suppose.
Mm.
Okay. So this is the village mean minus the block mean. You
Yes.
can define this is the block mean and this is the village mean minus the block mean, and this is the estimated treatment effect, which we have written by this alpha factor.
Yes. What is
And
the
then yes,
that is third one? What is it written?
this is the residual. This is what? This is the observation. How the observation, that means these three value, there are other two individual value. So
Yes.
how these three values differ from the other three values? That means what? Other three values means what? The other two values means what? That is the average values of all these three.
Mm.
This is we
What
call the residual.
what what is called extreme
Residual.
residual?
Am I audible perfectly?
Yes, yes, sir. I
Okay, okay,
couldn't heard. That's why I asked you.
okay. Now it is okay.
Yeah, okay, sir.
Okay. So in multivariate, when you are going to enter into the factor analysis, I'm telling earlier that is we are dealing with a huge data. Huge data set is there. So it is required for us data reduction. And the phenomenon, this PCA, that is the principal component analysis, where we are going to deal with, this is derived by Harold Hotling, and it is during 1933. So this is the basis behind the PCA. So a big data set. So start this. That is a big data set, huge data, and when it is a huge data, you get a huge variance covariance matrix. Because earlier I am telling you, already told you that is how the variance covariance matrix is construct. So you get a variance covariance matrix. PCA, that is when we are dealing with PCA, that is we have basically know the what is the significant, and that is how much significant independent variables, that is significant independent variables. What are the significant independent variables? Because why? Because all are not equally important. Okay, all are not equally important. So we have to deal with which are the significant and so why the data reduction. So we have to reduce our data. There are the several ways, not only the PCAs, that is, there are several ways you have to reduce the data. Otherwise, you may not reduce the data. You can generate the weights, for example, topsies, entropy. These are the different methods are there. So let us start with a three-dimensional situation, that is three variables, x, y, z. This is for your understanding, and you get the variance covariance matrix in this form. Surely you understand earlier there is a covariance between xx, covariance between xy, and covariance between yz, and covariance between yx, covariance between yy, and covariance between yz, and covariance between zx, covariance between zy, and covariance between zz. This is the variance covariance matrix, and when we are dealing with this software, it comes by this way. That is, suppose the values are 4, this is 3, this is 2, and this is 5, this is 1, and this is 4. This is the way, because these values are not same as 3, 5, and 1. So diagonal values are the variance, and the off diagonals are the covariances. If there are n number of variables, so look, there are 3 variables, so you get the combinations by between them, and the covariances is 0. That does not imply the variables are independent. You know that proof, but independent variables have the 0 covariance. That's the reverse thing. This is an important thing. And the off diagonal, if we look the off diagonal non-zero covariances, then there will be possibility of interdependence. For example, the off diagonal covariances are like this. So that means there are some level of interdependence. So suppose individuals, suppose we are dealing with n individuals, that means size of my sample, n individuals, and households actually. And basically they have the p character. That means p is the variate. Number of variable is p. So your data matrix or the data points, we rather call it, that is n cross p. And the matrix is like this. So p variables, mind this, these p variables are such that we cannot separate it in terms of dependent and independent. If we cannot separate or distinguish the p variate in terms of which one is dependent, which one is independent, then we go for multivariate. Mind it. This is a very, very important thing. Then we go for multivariate. When we are not making differences that which one is dependent and which one is independent, then we go for multivariate and then multiple regressions. But if there are n individuals, now we are asking about which individual is alike with the other individual with respect to particular variables. Is it possible to form some smaller number of groups or subgroups of the variables based on the similarity? There is the difference between multiple regression and multivariate analysis. So if we clearly split the dependent and independent variables, mind it, if you know that this is my dependent and those are my independent, then it is possible for you to do the multiple regression. But if you cannot split the dependence independence variables, that is, you collect some information on some character of the individuals or the character about something, but you cannot construct such a conclusion that which one is a dependent and which one is independent, then it is better for you to go to multivariate. So multiple regression and multivariate analysis are related, but in multiple regressions, one and each independent variable should have separate independent impact on dependent variable. But in multivariate, all sets of variables are related not in terms of dependent independence. So in multivariate analysis, we have to find difficulty to splitting the variate from others. So all types of multivariate analysis, if you go to the multivariate, that is dependence method, one dependent variable, and suppose it is given to you that this is a dependent and maybe multiple dependent, then you go to the dependent method. But if it is independent, that means you do not make sure that which one is dependent, which one is independent variable, then you go to the factor, cluster, or that is non-metric multiple discriminant and correspondence analysis, Latin structure, like this. So independence methods, that is independence methods when you consider that all the independent variables, when you are dealing with all variables are independent to each other, independent, we do not make differences between dependence and independence. We are considering our analysis that all are independent. Then one important problem, that is the multicollinearity. And we must be careful about this. PCA, what PCA is doing, that is basically combine some multiple correlative variables into a single index. And then we go for multiple regression. So data reduction is done by what? That is lowering the dimension. Or by another term, you may know it, that is the orthogonal transformation. And this orthogonal transformation, this new dimensions creations, or the transformed dimensions, are known as principal components. These are that means you have a data set, you have a data matrix. The process is very simple by how we are deriving principles. I'm not going to the process. I will come back. Suppose there are some processes. So by some process, you are lowering the dimension, and the process is known as orthogonal transformation. And by these orthogonal transformations, what we get, that is the principal components. This is the crux of the analysis. So, for example, suppose we have started with very simple and easy. Suppose this is two variables. We are dealing with two variables, and the data matrix is this. Suppose x11, x12, x21, x22. Later I'll deal with the data. But suppose it is start with this. So this is n number of observations. N is maybe the any number, and this is a data set. Now what I am doing, I just plot this data set in a graph. This is a basic and very interesting part of the analysis. Look at this. I just plot this data set. Suppose this is a data. These all values are the data. Suppose. And I just plot this data set considering measuring x1 here and x2 here. And you know this is the negative side of x1, these are the negative side of x2. And suppose when I plot the data looks like this. Suppose it is looks like this. So the data looks like this. Suppose I plot the data set, this data matrix. This is plotting, and after getting the plot, I get this data set. Now, after making such plots, we want to calculate the distances, that is the deviations rather. So for x1, look, this is the one positive extreme value. and this is the one negative extreme value. Suppose in general logic, this value is the extreme negative value and this value is the extreme positive. So the deviation of the difference is this. And similarly for the x2, suppose uh, this is the differences. So look at this black line and this green line, and that means you calculate the variances, covariances by this way, and the variability, rather we use the term variability. Now look, can you conclude anything from this variability? No. Basically it looks like if I put the scale or this kind of things, there may be some minor differences, but the variability is high. But the variability is there. Okay. So let us now do one thing. What I am doing, now I consider these two axes. Suppose these are made of threads, and I change this axis towards this. Suppose this point is uh, you just fix it by some threads, and you just change this axis in this direction, that is anti-clockwise, and the tilted one, the new axis becomes like this. That is, look at this new axis. Suppose it is known as Z1, and this is written as Z2. And how we get? We just changes this axis by the angle, suppose theta. So this angle is always theta, and that one is theta, and that one is theta. Everyone it is everyone by theta angle. We just switch the axis in anti-clockwise. Okay. Is the understanding is clear to all? Okay.
Yes, sir.
Now I just erase this black one. Okay, it is. And then go to measure the same variability by the earlier technique. So for x1, I found this is the extreme observation, extreme right, and this is the extreme left. Look at this, and difference or variability is this. But for x2, I found this is the extreme, and this is the minimum and maximum. So the variability is this. So look, by changing the uh, dimensions by angle theta, I found from this data set that x1 have some greater variability in compared to x2. or rather you may say not x1, now it is changed to z1 and z2. So z1 have some greater variability in compared to z2, but in our, as per our earlier figure, we found that the variabilities are remain same, or more or less we cannot conclude anything. But just switching the figure by angle theta, we find out that the variability of the first variable, or that is new or new reformed variable z1, is greater in compared to z2. Is it okay to all? Is the understanding?
Yes, sir.
This is actually the PCA doing. Here we have started with two variable case, and it is signaling us that x1 is more important in compared to x2 because it has some greater variability. And this is PCA is actually doing this, that is as per the variability, rank the variables or the components. So there are some middle level mathematics, and I'm not going to that. What we are doing actually, just recall this picture. That is, now the variables are not in terms of the x1 and x2. Variable is changes because it is x1, from x1 we switch over the angle by theta, and we get the z1 and we get the z2. So the transformation is something kind of made. And what we get, that is a simple mathematics is there. That is, what is the relation between x1, x2, and z1, z2? This is the relation. There is a relation. It looks like this. That is, z1 is x1. That z1 is interpreted as x1 cos theta plus x2 sin theta, and z2. Those who are not familiar with these trigonometry kind of things, they may not interested. But those who are uh, maybe interested, they for better understanding actually, this is the relationship. What is the relationship between, because otherwise I have not give you the sense that how x and z are related. So this is the relationship, and you may write it in terms of matrix vector rotation, my notation. That is, we write it as this. By the way we solve the equations. So you do not look this theta kind of things. This is something that is by what amount the angle is changes, the values come to by that way. So ultimately, what we are doing, I write it as a matrix A, this matrix, and in the form of the transpose. This is A transpose X. And what is A? A is this. That is cos theta minus sin theta and sin theta and cos theta. Because why this is minus sin theta? Look here, it is originally, this is written as A transpose. That means row in place of column and column in place of row. So originally we write it as A, and this column and that column, this you can write it as in the form of A1 and A2, and this is the background of the A matrix. And so for mathematical purpose, when you are solving this A matrix can be converted, or can be written as in the form of A11, A21, A12, and A22. And basically this is the A1 and A2. This A1 and A2. And what is A11? That is the cos theta. What is A12? That is the sin theta. What is A21? That is the minus sin theta. And by this way. So look at this. Look at this expression. That is A1. A1 means this, and A2 means this. So look the beauty. That is A1 transpose A1. That is what A1 is cos theta, and its transpose means column goes to the row space, and the A1, that is the cos theta sin theta. So it becomes cos square theta plus sin square theta. That is 1. So it is always happen. Similarly, A2 trans. Why I am dealing with this? Because these results are important in PCA, and this is also 1. And not only this, for the whole of this matrix A, these results will hold. That is A transpose A is equals to 1. So A is a symmetric matrix, and this A transpose A is an identity matrix. So this will holds true. That is for two number of variables. Then if we increase the number of the variables, the relationship will get by this way. That is this we get, suppose for example, this relation, that is Z is equal to A transpose X. And if I break this relation for the first variable, that means Z1, that is Z1 will be what? That is A1 transpose X. That is what? That is A11 X1 plus A12 X2 and so on, plus A1K XK. And similarly you write Z2, and similarly you get ZK. So these are the principal components. This is what we are doing. That is, we make the combination, not the variables. Z1 is the first principal component, Z2 is the second principal component, and ZP is the pth principal component by this way. So look, what is important, that is, when you interpret the results, Z1, which is the first principal component, and which carries, it is arranged by such a way that it carries the maximum variability. That means it is the most important. Z2 is the second principal component, which is the next maximum variability. That means if for example you write it as Z1, that is is the first principal component, carries the maximum variability among all. You may write it among all principal component Zj, where J is equal to what? 2, 3, and so on up to suppose K numbers. And what will be the when I am right here among all J, this is the second next means, because first one is already we have chosen, it is done. So among all J, but J is started from where? That is started from 3, 4, and dot and K, and Z3 is the third. So by this way, it gives us the list of the principal component where the variance of Z1 is the highest, and next to variance of Z2, and next to variance of Z3, and so on. And for such things, what is important to us, that is for such variability, important thing is for any AJ transpose into AJ is equals to 1. This is the important thing. That means I'm just giving you the sense, that is Z1 is the first principal component, suppose, which explains, suppose, 66% variability of the data matrix, and Z2 is the second principal component, which explains, suppose, 22% of the variability. Z3 is, suppose, 5% of the. By this way, the explanation variability, power of explanations of the components are reducing. So uh, so already how much time we have? 50 minutes. I think we have 50 minutes now.
Yes, sir.
Okay.
Yes, sir.
So okay. So this is the important part of the principal components, and this is how it is working. That is, we have to derive the different principal components on the basis of this relationship. So What is important part is that if S is the, if you know the S is the, sorry, variance, I'm not going to the calculation, variance covariance matrix, and we have to calculate that S minus lambda I, and if we get that this determinant, set this determinant equals to 0 for the unknown values of lambda, and these lambdas are called eigenvalues. These lambdas are called eigenvalues, and different eigenvalues we are actually going to deal with. So first, I will just wait. I will go to uh, SPSS. Just 1 minute. Just 1 minute. I will change the my. Yeah, my the screen is visible. I'm started just with a there are actually I have to show the two examples. First one is very simple for your understanding, and then one is more complicated data set. Then one is with a larger number of variables. So there are the two variables. Suppose some any kind of informations. There are 12 data. These are actually in theoretically it is not applicable for the PCA because norms will be not validated. So the informations are on SPSS windows. It is the information on food and smoking. So suppose the information are 12 variables and I have to go to the uh, PCA. So you just note down the steps. What you will do, we will go to analyze, and when I click on analyze, uh, there is one that is the dimension reduction. You find this, and then your step is go to the factors. Okay, so three steps are like this: analyze, then go to the dimension reduction, and then go to the factors. Then you select the two variables, and I just incorporate the variables into this part. So just 1 minute. Then you find out that there are the different descriptives, extractions, rotations like this. So you first go to the descriptives, and there is already the click on initial solution under the statistics menu. And in case of the correlation, you just go to the Kaiser. That is KMO Bartlett's test of sphericity. I will come to that. What is that? That is the KMO test. I will come to that later. But just you know how to extract the solution first. Then click on continue. Then the descriptive part is done. Then you go to the extraction part, and in extractions there is it is the we are interested in correlation matrix, but rather here we are interested in covariance matrix and the unrotated factor solution in the display and the scree plot. I click on it because scree plot. I actually explain the nature of the scree plot in our second example, and based the extraction is based on the eigenvalues, and it is continue. Then go to the rotation, and when you go to the rotation, you obviously follow not on everywhere that there is direct oblimin and there is varimax, and we suppose we follow the varimax, and then the solution, rotated solution, it is already display, it is already ticked, and then the scores, and it is a set as variables, and uh, display factor scores coefficient matrix, this one, and then continue, and then options. And when I consider the options, that is uh, uh, exclude in the missing values, exclude the case list wise. This is already given, and the coefficient display, that is sorted by the size, and suppose suppress the small coefficients. Up to it is given up to zero point 0.1 g, that is 0.1, but suppose we are considering up to 0.30. This is the uh, important, that is absolute value of the coefficient, correlation coefficients. These are greater than 3.3. It will be identified that they are very much relatively related. So we can make the continue, and the output will be produced. The output is very simple. This is the first is the KMO Bartlett test, sample adequacy, which is required at least greater than 0.5. Mind it. Oh, this is not 1 minute. Just you are not. 1 minute. I will display. Yes, this is the output produced, and you look at the first, that is game of Bartlett test. That is here. That is Kaiser-Meyer measures of sample adequacy. That is 0.5. But it is always you note that the KMO validity, the values is always be when it is accepted a good model or good model to run the PCA. It is obviously it will be greater than 0.6. So it is not a very good model. Our data set is not very good to run the PCA. But the Bartlett test of sphericity is become significant. That is not important to us. What is important to us? That is just remind this for these results I am actually showing. That is look the eigenvalues. That is 30.661, which explains the 99% of the first principle. That is first component, which explains the 99% of the data set. And the second component, which value is 0.038 or 0.028, it is close to 0.03, and it explains only 0.9092 of the variances. So this for these two results, I am actually showing you these examples. Now my question is how these eigenvalues are actually from where it actually comes, how these eigenvalues are estimated, how these values are, what the values are actually showing. And in terms of the extractions, look, this is in cumulative percentage. This explains that 99% of the variability is explained by the first factor. So how it is important? The second factor is least important. It only explains 0.092% of the data. So uh, um, this is the thing we are actually going to note down here from here, that how these eigenvalues are generated. Then I come to the second that is, uh, example. So let us back to our previous one. So the data set is you already. I'm just write the data set what we are dealing with. That is the values are like this: 10, 100, 12, and 110, and 11, and 105. By this way, 12 data set, 12 values are there, and the last value is 12, and it is 110. This is our data matrix, which is actually already shown in the first screen of the PCA. Now look, that means what? This is the x1 and this is the x2. So like before, you can find out what is mean of this, what is mean of this, and similarly you can find out what is S11 and what is S22, and you also find out S12. Okay, so the covariance matrix, if we calculate the covariance matrix from this data set, you may calculate this. It is for the food and smoking. The values are like this. That is 1.15, and it is 5.76, and it is 5.76, 29.54. I'm not showing the calculation, but I think you know that. That is how to calculate this. This is the variance of the food, and this is the variance of the smoking. And now this is the covariance between the food and smoking. So we get the covariance matrix. Now just in our SPSS results, what we get, I just write the results. The eigenvalues are like this. That is for the first component, it is 30.66, and which explain in terms of the proportion, that is 0.99, and cumulative proportion This is 99.9%, and this value is 0.028. That means actually consider this is 0.03, and it is explained 0.0999. Actually, this is explained 0.001. So that means 0.1%. This is the result. Uh, so how these two values comes? So looks this. That is, what are the principal components actually? What are the PCs are actually? So how this is derived? So look, I am telling earlier you that this is the important thing: variance, covariance minus lambda I, where lambda is the eigenvalues. So how it is estimated? I just going to show you. That is, I have to calculate S minus lambda I, and this equals to 0, where S is what? That is 1.15 and 5.76, and this is 5.76, and this is 29.54, and I is what? This is identity matrix, and therefore this construction, this one becomes, that is 1.15 and 5.76 and 5.76, 29.54, this minus lambda into 1001, and in this total term in the determinant form, and this is equals to 0. So if we go to calculate this, just look at this matrix subtraction rule, and it becomes like this: 1.15 minus lambda and 5.76 and 5.76 and 29.54 minus lambda, this equals to 0. So you just matrix multiplication rule, you know, this multiplied by this and this multiplied by this. So the result becomes 1.15 minus lambda into 29.54 minus lambda minus 5.76 whole square equals to 0. And you just calculate this equation, and when you calculate this equation, you just get a quadratic equation, that is in terms of the lambda. And what is the form of the quadratic equation? You just, if we solve this, it's like this: that is 30.69 lambda plus 0.7934. So it is an equation from where we can solve the two values of lambda. One is lambda 1 and another is lambda 2, applying the Subhasis rule, and the values is this 30.66 and 0.03. These values are actually showing there. These are the eigenvalues. Okay. So these are the two eigenvalues, and now how this earlier derived this AJ transpose AJ is equal to 1. How the AJs, that is the principal components, are derived. How the principal components we get from this equations. That is for the first lambda, for example, for the first lambda, the values is 30.66, and if I put these values of lambda here in this equation, look what I get. That is 1.15, 5.76, 5.76, and 29.54 minus 30.66. That is the values of lambda 1. This value, in place of this lambda, I put the value of first lambda, that is 30.66, into 1001 matrix and this is multiplied by A1, we get the 0. And what is A1? Mind it, what is A1? That is A11 and A12. So look, uh, these values becomes 1.15 and 5.76, 5.76, 29.54, this minus 30.6600, 30.66, and this into A11 and A12, this equals to 0. And from solving this, we get this, that is this part. If we solve, the matrix will be followed like this: minus 29.51 and 5.76 and 5.76 and minus 1.12 into this A11, A12, this equals to 0. And from this directly, you know the rules of matrix multiplication. This multiplied by this is the generate the first equation, and this again multiplied by this generate the second equation. So the two equations are generated by 1 minute. Two equations are generated by minus 29.51 A11 plus 5.76 A12 is equal to 0, and 5.76 A11 minus 1.12 A12 is equal to 0. So we do not get the solutions of A12 and A11 from these solutions. So what we will do, we have another weapon. The weapon is this, that is, where it is, this. This is the weapon, that is A1 transpose into A1 is equal to 1. That means we have the thing like this, that is A1 transpose into A1 is equal to 1, which is actually means A11, A12, and this is A11, A12 is equal to 1, which actually means A11 square. Multiplication rule of matrix, and A12 square is equal to 1, from where we get A12 is equal to root over of 1 minus A11. So if we put the value of A12 here, that is root over of 1 minus A11, then from here we can get the values of A11. And similarly, when you get the values of A11 into these equations, from these two equations, from the first equations, if I put the values of A12 is equal to root over of 1 minus A11, then transferring this term in the other sides, we can solve the value of A11. Actually, if you're interested to this example to find out the value, the values become 0.19, and A12, if we solve, these values is 0.98. So what is the meaning of this? That means when the eigenvalues is 30.66, we get the two factor loadings. These are actually also in the second example. For understanding, it is important. The first factor loading is 0.19, and the second factor loading, first two factors, that is 0.98. These are the two factor loading. And similarly, if you put the value of lambda 2 is equal to 0.028 or 0.03, you can find out the two factor loading as A21 and A22. So from this, you can get the values of A21. If this example, if you calculate the values is 0.98 and A22 is minus 0.19. If you solve this example. So I'm not looking at into the what are the answers, but actually these are the way to interpret the results. So the principal components. So the first principal component is what? That is 0.19. That is the value of A11 into first variable x1 plus 0.98 into the second variable, that is x2. And similarly, Z2, that is 0.98 x1 and minus 0.19 x2. These are the two principal components we actually get. So, you know the results, earlier results, that is KMO. model adequacy and model adequacy interpretation, that is interpretation. I'm coming to the next example after that. Before that, interpretation is very important. Interpretation of model adequacy. So you get, that is lambda 1 is what? 30.1st eigenvalue, this, and the second eigenvalue is this. So look, what is the value of summation of lambda j? That is 30.66 plus 0.03, 30.69. So actually we have extracted lambda j from the S matrix. Mind it, the S matrix is what? There is a variance covariance matrix 1.15, 5.76, 5.76 and 29.54, from where we extracted the lambda 1 unit. So look at the trace of S matrix. So what is the trace? Trace means the diagonal terms, diagonal elements of the trace of any matrix. Mind it, trace, that is actually we write it by this way, that is here S, that is trace. Trace means what? That is the sum of the diagonal terms. So trace of S, which is what? 1.15 plus 29.54, and look at this, this is 30.69, that means summation of lambda j. So we can say that this trace of S is summation of lambda j if it is whole for the PCA. If it is whole for the PCA, that is the sum of the trace of the variance covariance matrix is equals to the sum of the eigenvalues. Then we can say that variability extract of the maximum of the eigenvalue, the sum of this is equals to the sum of the variance components of the original matrix. And if this is holds, then the results is it is called that is the model is adequate. So that means what? That means what is happening? Look, what are the first principal components we get? This, look at these two values. These are the first principal two components, 0.19 and 0.98. So considering this, if you also calculate, that is A1, sorry, that is if you calculate A1 transpose S A1, that means 0.19 and 0.98 multiplied by the variance covariance matrix, and this is 0.19 and 0.98. Then you solve this, the values will be this, the first eigenvalues. So then you say the model is adequate. Now there are different tastes about the inference of the PCS. I'm not going to that time. One important test, that is the Bartlett's sphericity test. So what is Bartlett's sphericity test? The result will come into the table, but I'm just giving you the meaning. The X is the data matrix, and which is consist of p variables. Mind it, we started with such. Suppose here we are considering an example that two variables. So after extracting, after running the PCA, when we run the PCA, we get m components. That is equivalent to p, but all components are not important to us. So in case of two variables, if the plot is like a sphere, earlier example, if the data are plotted by this way, then you change the direction, then you change the dimension by theta, and we found that that this dimension change will have no impact on the variability. So there actually the Bartlett test is working, the relationship between the variables, and it is actually there are some it follows some chi-square distributions, and I'm not going to that distributional part. So that is we actually consider the data is in the form of the sphere. If it is form of sphere, then making some losing some dimension, it is not gives us a meaningful result. But what we actually Bartlett's sphericity test is doing, that is assume the data is sphere and prove that the hypothesis will be accepted that the data is not a sphere. So if it is okay, that means the significant. Then the thing is that is yes, the data set. That means we change the dimensions and we get the number of variables is reduced, and the number of variables can be arranged in terms of the variability. So there are the different process, that is how to consider which up to which eigenvector values we have to consider. That means how many variables are important to us, and that will be chosen from the results of the eigenvectors. So some rule is average root. That means how many eigenvectors you get, you find out the average values. And there is another Kaiser rule is also there, and which is consider of the correlation matrix and its trace values. And there are the different broken stick method is there. Regarding how many there are, when you have so many variables. Look, when you have so many variables, in case of many variables, you get many lambdas. So which lambdas, up to which lambdas you have to choose. And there is one plotting, that is the scree plot. What is scree plot actually shows to us, that is up to which values of the lambda we have to chosen. That is how many, up to what dimensions we have to consider. So let us it is better for us, that is to go to the second example, because there is time is also I'm sharing from my laptop. So just wait 1 or 2 minutes. Is the data set is visible to all in SPSS? I think it is okay, na?
Yes, sir.
Yeah. Actually, the data set is randomly chosen. It is those who are from the social science background. This data set is a village-based information of Purulia district, where I am actually working, and this data set is from the DCHB. It is a DCHB based data set of Purulia, and the name of the villages are there, and the residents and residents are the residents. These are the percentage. All data set are in the form of percentage. Residence, that means residence means, just 1 minute, I describe the variables to you for your better understanding. That is livable condition of residence. This is the first variable, and the livable condition of residence and other use, that is the thing that is rented out, or this kind of things. And third one is the concrete roof material, concrete wall, that is cement floor, household size, household own the house, tap water from the treated source. And if you open the DCHB data set, you get this. Within the premises, drinking water availability, electricity, number of households having latrine facility within premises, have a pakka bathroom, closed drainage, LPG and PNG, a separate kitchen, number of households. That is, if I go to the variable view, it will be clear to you. These are the variables. So number of households having banking service, radio, transistor, television, computer, internet, mobile, bicycle, scooter, car, and the permanent resident or not. So these are the variables, and the data set is
This
data set is,
data to us?
pardon.
Did you send this data to us?
It is available to you, madam. It is not necessary that I have to send you. You just open the Google and type the DCHB dataset. In which districts you have to belong, or you can identify your working area. Then you can it is available in the Excel format, no difficult. So you can easily get it. It is meaningless whether I am sending you the DCHB because it is the central government dataset, and you just type DCHB dataset. Okay. So
Oh,
you get it. Otherwise, if you require, I sent it to the Shankar Babu, and then you will get it from. Okay. So this is the data set and percentage data set, and here we are uh, going to uh, analyze. That is, the screen is visible now.
Yes, sir.
Okay. So analyze like before, then dimension reduction, and then factor. So village is a string variable here, and we do not consider it, and remaining the variables, all variables, I transfer it here, and the descriptives, in case of the descriptives, uh, that is KMO Bartlett test of sphericity. Then we have to go to extraction, and here in case of extraction we are consider the correlation matrix and scree plot and unrotated factor solution in the display. Uh, so then we consider the rotation, and we follow the Varimax and the rotated solutions, and we uh, continue. Then we consider the scores and save as variable and display factor scores coefficient matrix and continue. And then we have the options, and it is sorted by size and supplies the small coefficients, that is 0.3. Actually, it is written as and continue, and it is okay. So the output is generated. So look at the first table, that is KMO Bartlett test results, where the sample adequacy, it is the value of KMO Bartlett KMO measures that have sample adequacy is greater than 0.6. I am telling earlier you is greater than point. It is here 0.905, and it is found that the Bartlett test of sphericity is also significant. So it is one kind of okay. So now uh, we go to the look at the variance, and that is the total variance explained. So you find that the first component, that means the Z1, whose value is 7.046, and which explains the 29% variability of the data set. So look at this. And the second component, its value is 1.720, which explains 7.166%. And 36.524 is the cumulative explanations of variance of the first two factors, first two components. So by this way, we found here that is up to 6. It is better to us. That is these are eigenvalues are greater than 1. That is first 6 components we have found that the eigenvalues are greater than 1, and then it is that is a look at the cumulative percentage of explanation. That is up to 6. It is becomes 56 now, then becomes 60, then becomes 64. So there is a small variation. So only the first factor you find that it is totally explained the 29%. There are some questions actually. There are those who are try to make their analysis more pure. There is some questions in SPSS because SPSS is not ready to produce these kinds of things. Look at the fast factor. Its value is 7.046 and 29.358% is variance. It is explained, but there are some Monte Carlo simulations of principal component. There are some software is available, which actually where we actually have some predictive type of analysis. That is how many eigenvalues are greater than 1, like this. There you actually find out that from that kind of software analysis the results will be that is like here factor 2 or factor 3, component 2, component 3, component 4, and component 5. These are quite okay rather, but first component it is explained 7 point, it is values is 7.046. It is quite high. So sometimes it is questionable. That is how it is uh, how it is only it is explained the 29% how much it is. So okay, now for the initial part, this is okay. So you have to look after the factor that the KMO values, it must be greater than 0.6, and Bartlett test is significance. So then you go to check the correlation matrix. So where it is probably we do not choose it earlier. So look at the scree plot first. So look at the scree plot. So changes of the graph or the elbow is where that is you find that first after the first 3 factors, first 2 factors. Let's just consider the factor 3 up to the factor 3. And its component number is in the horizontal scale, and there is a huge fall. So that means first 2, at least the first factor, is explained heavily the data sets. So first component is explained heavily the data sets, and the second factor and the third factor are quite close, and after that this becomes more or less a slightly downward swing thing. So though we have to find out that from the earlier explanation that the 6 components are eigenvalues are greater than 1, but the scree plot what is showing us that is that there is a sharp decline after there is a sharp decline in case of factor 1 and factor 2. So yes, that is the component matrix. Yes, look at the component matrix. That is the first component chooses the which variables. It chooses the floor material, it chooses the televisions, it chooses the roof material, bathroom, and uh, values are these values are that is these variables are quite significant. That is look, bathroom use habit, it is 0.816 the component value, and for the second component, look, the bathroom use habit is minus 0.374. So look at this, look at these values of the second component, these components. So first component, regarding the first component, we can say that on the basis of the highest loading values, it generates some positive effect, and component 2 generates some negative effect in terms of highest loading value. So negative, that means the lowest value is that is LPG, that is the point minus 0.393, and the value of the bathroom use habit is also quite low, that is negatively low. That means it is a significant factor. That is, you have to identify that is the bathroom use habit is gives us and some important variables over such set of 15 or 16 variables is there. So by this way, considering the eigenvalues, that means from here what we are getting, that the first component which only explain the 29% variations of the data set, it consider that these variables are quite significant for your analysis, and it can make the arrangement of such variables. You can find out the bank account. That is, you can choose there. You can choose in terms of their value. That is floor material. It's explain the point. Its value is 0.865. It is the important factor. That is floor material. Original variable is known as floor material. Is by cement. This is an important variable. Television is the next important issue. Roof material is the third important issue. This is the important principal components what we have to do with uh, that is selections of such kinds of variables can be done with the help of the principle. So one thing is important, that is I'll sum up by this after this make such component comments, that is process of uh, that is handling of software is quite easy for the PCA of this, but you have to know the background working of mathematics, how it is working, and then it is easy for you. That is why the eigenvalues are important. Why the what is the when the model adequacy is this, that is the stress of the variance covariance is whether it is equivalent to all sum of eigenvalues, then we say the model is adequate. So I'll stop here, and if you have any questions or this, you may ask. I think it is a huge topic, so it is better always that you have to go through the uh, smaller amount of mathematical background first, make it clear, make it sound, then you go to the